In this video, we are going to talk about probability rules, and we're going to look at the addition rule and then the complement rule, and then we're going to look at some combinatorics and combinations. So let's start with the addition rule. So our rule is really going to depend on whether or not we have mutually exclusive events. So what does that mean? Two events are mutually exclusive if they cannot happen at the same time. So that means that the probability of A and B, one event that has both characteristics happening at the same time, would be equal to 0. So what are examples of things that are mutually exclusive? Let's talk about flipping a coin. So if we were to flip a coin, we are either going to get a heads or we're going to get a tails. We cannot get one flip that's both heads and tails. So those events would be mutually exclusive. Let's say we're drawing M&Ms out of a bag of M&Ms and we want, and maybe it's a mix of peanut and plain. Well, the events peanut and brown are not mutually exclusive because we do have M&Ms that are brown peanut M&Ms. So what would our rule look like? So events are mutually exclusive. We have the probability of A or B. So now we're looking at the probability of or, means the probability of A plus the probability of B. So let's look at an example. Suppose a single card is drawn from a standard deck of playing cards. We want to find the probability of drawing a 5 or a king. So let's talk about what a standard deck of cards looks like. So in a standard deck, there are 52 cards, and the cards have 4 suits. There are diamonds, there are hearts, there are spades, and there are clubs. These are red cards, and then these are black cards. And each suit will have an ace, a king, a queen, a jack, 10, 9, 8, 7, 6, 5, 4, 3, and then 2. These, king, queen, and jack, are called face cards. So let's say we want to find the probability of drawing a 5 or a king. So it would be the probability of a 5 plus the probability of a king, because these are mutually exclusive. Which means that we cannot draw one card that is a 5 and a king. So the probability of drawing a 5, there's going to be 4 5s, one from each suit, out of 52. And there's going to be 4 kings, one from each suit, out of 52. So my total would be 8 out of 52. And if we reduce that fraction, that would be the same as 2 out of 13. So how would that change if the events are not mutually exclusive? Well, our rule is going to have to accommodate the probability of A and B. So it's going to be the probability of A or B is going to be equal to the probability of A plus the probability of B minus the probability of A and B. So let's change our example up here. What if we want to find the probability that it is a 5 or a heart? So it would be the probability that it's a 5. There's 4 out of 52 that are 5s. Okay, and that includes 1. Well, hold on a minute. And then we have 13 out of 52 here. Now this 13 is going to include a 5 of hearts, okay, which is also included here. Which means we're going to have to subtract the probability of that combination. Because the way that I could get a 5 is I could have a 5 of diamonds. I could have a 5 of hearts. I could have a 5 of spades. or I could have a 5 of clubs. So those are the ways I could get a 5. And then out of my hearts, I would have all 13 of these. But you can see that that 5 of hearts is going to be included twice. So that's why we have to subtract it once. So we're going to have a total of 18 out of 52, which reduces to 9 out of 26. So that's how our rule will change for that. All right, so let's look at a few examples. And this is where you may want to pause the video, try these, then come back and then check your answers. So here's some examples from the end of this section in the textbook. Number 2 is asking the probability that that if we draw a single card, find the probability of drawing a heart or a club. We're drawing one card and we want to know the probability of a heart or a club. These are mutually exclusive events. So our probability would be the probability that it's a heart plus the probability of a club. So we have 13 hearts out of 52 plus 13 clubs out of the 52. So that's 26 out of 52, which reduces to 1/2. So you have a 1/2 chance of, if you draw one card randomly from a shuffled deck, that's either going to be a heart or a club. Let's look at number 3. We're rolling 2 dice now. We want to find the probability of rolling a 2 or a 10. Remember, this is a sum of 2 and a sum of 10. So if we think about rolling our dice, I'm going to go down here and I'll list the sample set. So here's our sample set, and I did pause the video and write all this down. We want to know the probability of rolling a 2 or a 10. So a sum of 2, there's only one way that can happen. And then a sum of 10, there's 3 ways that can happen. So it's going to be 1 out of 36 plus 3 out of 36, which is 4 out of 36. And that's going to reduce to 1 out of 9. Okay, now remember, these are mutually exclusive events. I can't roll 2 dice and get both a sum of 10 and a sum of 2. One of those things could possibly happen. 4 is going to work the same way. We want to find the probability of rolling a 7 or an 8. So we just count how many ways that's going to happen. Again, they're mutually exclusive. So here's my probability of rolling an 8. And then here's my probability of rolling a 7. So there's 6 ways that I could get a 7 and 5 ways that I could get an 8. So there's 6 out of 36, that's the probability of rolling a 7. 5 out of 36 is the probability of rolling an 8, for a total of 11 out of 36. And the next few examples, they are giving us probabilities, and they're asking us to find the probability of A or B. So let's do a couple of these. Number 5, they tell us the probability of A is 0.2, which is 20%. The probability of B is 0.5, which is 50%. And the probability of A and B is 0.1, which is 10%. We want to find the probability of A or B. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So it's going to be 0.2 plus 0.5 minus 0.1, which is going to be 0.6 or 60%. Now let's change it a little bit. Let's look at 7. 7 tells us the probability of A is 0.3, the probability of B is 0.8, and the probability of A or B is 0.9. They want to know what's the probability of A and B. So let's use that formula and let's substitute everything we know into it. So probability of A or B is 0.9. The probability of A is equal to 0.3. The probability of B is equal to 0.8. And we want to know the probability of A and B. So I just plugged what I knew into this formula. And now I've got this little mini equation to solve. So 0.3 plus 0.8 is 1.1. A and B. So let's subtract the 1.1 from both sides. 0.9 minus 1.1 is negative 0.2. And then if I divide both sides by a negative, there's my probability of A and B. So I could use the given information to find any of those four pieces. As long as I know three of them, I can find the fourth one. Let's look at number 8. They gave us the probability of A and the probability of A and B and the probability of A or B. Now they want us to find the probability of B. So let's plug everything we know into this formula. So the probability of A or B is 0.8. That's going to be equal to the probability of A, which is 0.7, plus the probability of B, which we don't know, minus the probability of A and B, which is 0.4. So let's clean this up. 0.7 minus 0.4 is 0.3. And if I subtract 0.3 from both sides, my probability of B would be equal to 0.5. Let's do a couple more. So in this set of exercises, 2 dice are rolled, and we want to find the probability of each of these. Let's say we want to find the probability of a 6 or doubles. And that's talking about the sum again. So the probability that we're going to roll a 6, if we go back to our sample set here, there's 1, 2, 3, 4, 5 ways that could happen. The probability we're going to roll doubles would be down this diagonal. There's 6 ways that could happen. But notice that when we did this, let me see if I can circle these. So there's my doubles. And then let me change that color. You see how this one gets circled twice? That's why we have to subtract, because we don't want to count it twice. It just wouldn't be fair to count it twice. So my answer is going to be 10 out of 36. And we can reduce that. That reduces the 5 out of 18. Okay, so we're using the same formula that we did before. Let's do one more of these. Let's look at 16. We want to find the probability of rolling a number that's greater than 7 or rolling doubles. I'm going to go back to my set up here. So a number greater than 7, that would be a sum of 8, 9, 10, 11, or 12, or getting doubles. One roll where this could happen. So let's just count how many there's going to be. So the sum of 8 would be here. There's 5 ways that could happen. So I'm going to write how many ways it could happen above here. 9, there's 4 ways that could happen. 10, there's 3 ways that can happen. 11, there's 2 ways that can happen. And 12, there's 1 way that can happen. And then doubles That would be the 1, 1, the 2, 2, the 3, 3 down that main diagonal again. There's 6 ways that can happen. But now we got to take out that overlap. So where we get one of these sums and we got that sum using doubles, well, that's going to happen here where we would have an 8, here where we would have a 10, and here where we would have a 12. So we're going to subtract those 3 ways. So let's look at our probability. We have, if I add these together, 5, 15, 36. So the probability of getting one of these sums would be 15 out of 36. Probability of getting doubles would be 6 out of 36. But there's 3 ways where both of those things happen at the same time. These are not mutually exclusive events. So we're going to subtract 3. So 15 plus 6 minus 3 gives us 18 out of 36. And that's going to reduce to 1/2. All right, let's look at a contingency table. So with a contingency table, the first thing I like to do is add everything down the columns and add everything across the rows. So we're going to do that. So I got 5. It keeps wanting to select my picture there. 559. 36. 442. 864. 778. This column is 1581. This column is 775. $823. I'm going to put that total in the box. So when I add these 3 numbers, it should be the same as when I add these numbers. That would give me my total. So let's look at 25. If a person is randomly chosen from the town's population, what's the probability that a person is aged 26 to 34 or is employed part-time? So notice these are not mutually exclusive because we do have some in that age range that are employed part-time. So we're going to find the probability that they're aged 26 to 34. So that would be 442. So that's all of these. And then we're going to add the probability that they're employed part-time. So that's 775 out of 3179. And so when we look at that, that's these. But notice the 67 got counted twice. So we are going to subtract the 67. Oops. Out of 3179 because we can't count them twice. It's just not fair to do that. That's why that formula is set up that way. So 442 plus 779 minus 67. I got 1154 out of 3179. So there's our probability for that. Let's look at 26. If a person is randomly chosen from the town's population, what's the probability that the person is at least 50 or unemployed? So let's read that one. I'm going to see if it'll let me erase the highlight here. So at least 50 would be this, or unemployed would be this. So at least 50, that probability is going to be 778 out of 3179. Unemployed would be 823 out of 3179. But notice that 173 got counted twice, so we're going to subtract it. I got 1428 out of 3179. So let's talk about our complement rule. Complements just means it didn't happen. So if the probability of an event happening is 1, let's say the probability event A happens is equal to 10%, which is 0.1. Then we want to find the probability that A did not happen. So we could use this notation that means complement. Some textbooks will actually write it this way with a line over it, but they both mean the same thing. So if you have a 10% chance of something happening, then the chance that it doesn't happen would be 90% or 0.9. So let's look at an example. The probability of tossing a sum of 11 on a toss of 2 dice is 1 out of 18. What's the probability of not getting a sum of 11 on 2 dice? So if we know that the probability is 1 out of 18, and that comes from the fact that to get an 11, we could have a 6 and a 5 or a 5 and a 6. So there's 2 ways out of 36, which is 1 out of 18. So that's where that came from. So what's the probability that it's not 11? So it's anything but 11. Well, it would be 1 minus 1 over 18. And we could write that 1 as 18 over 18 minus 1 over 18. And that's going to be 17 out of 18. So that's the probability of the complement. And then the last thing we need to talk about is combinations. Before we move on to combinations, let's look at this one. This is going to use the complement rule too. So a single die is tossed 4 times. We want to find the probability that a 6 is going to show up on the upward face at least once. We can use that complement rule to help us. So the probability, let's let E be the event that we get at least 1 6. So then the complement would be no 6s. So if we're tossing it 4 times, let's figure out how many what would that denominator be? So that's going to use what's called the fundamental theorem of counting. So there's 6 ways that when I toss a die, I could get a number. And then when I toss it again, there's another 6 ways. So that's how many ways I could toss to get outcomes if I roll 2 dice. And that's where the 36 came from that we talked about before. And now we're going to toss 3 and then 4 times. So my total number of outcomes would be 6 times 6 times 6 times 6, which is 1,296 possibilities. So this is going to be my denominator. So we've just got to figure out how many ways I could have no 6s. Well, on that first roll, as long as I get a 1, 2, 3, 4, or 5, I would not have a 6. Same thing for the second roll, same thing for the third, and then same thing for the fourth. So 5 times 5 times 5 times 5 is 625. So the probability of getting no 6s would be 625 out of 1296. We want to know the probability of getting at least 1 6. So that's going to be 1 minus the probability of no 6s, which is 1 minus 625 out of 1296, which is going to be, so this is going to be 1296 over 1296 minus 625 out of 1296. So I got 671 out of 1296 for that one. So now let's look at combinations. So combinations is a way to count how many ways items can be rearranged if order doesn't matter. So think about like a combination pizza. It doesn't matter how I arrange the toppings on there. Order is not important. As long as I get all my toppings, I'm happy with the outcome. This exclamation point is a factorial sign. It means you're going to multiply all the numbers, whole numbers, from whatever that number is down to 1. So for instance, 5 factorial would be equal to 5 times 4 times 3 times 2 times 1. So our combination formula would be n factorial over r factorial times n minus r factorial. So let's look at an example. Suppose a manufacturing process for tableware produces 40 dinner plates, of which 3 are defective. If 5 plates are randomly selected from the 40, what's the probability that at least 1 is defective? So we're going to use that idea that we talked about before with complements to help us solve this problem. But we've just got to count how many ways it is. And it's as simple as when I roll a dice 4 times, counting how many options there are. It's a little bit more complicated in this case. And that's where the combinatorics is going to come in. So first we got to figure out from the 40 plates, how many ways can I select 5? That's going to be my denominator. So it's NCR. So it's 40, choose 5. So it's going to be 40 factorial over 5 factorial, 40 minus 5 factorial. So 40 factorial divided by 5 factorial, and this would be 35 factorial. So this would be 40 times 39 times 38 times 37 times 36 times 35. And we would keep going, 35, 34, 33, 32, 31, and so on, which is the same thing as 35 factorial. And notice I would stop there because I've got a 35 factorial in that bottom. And they're going to cancel. And then 5 is 5 times 4 times 3 times 2 times 1. So let's start canceling some stuff out. So there's 35 factorial, which are going to cancel. 5 times 4 is 20. 20 times 2 times 1 is a 40. So that's going to cancel with that. And that 3 will reduce with that 36 12 times. So I've got 39 times 38 times 37 times 12 left. And that's the number of ways that that can happen. 658,008. Now, I could do this in Desmos also. I could type in 40 factorial divided by 5 factorial, 35 factorial, and it's going to give me the same answer. So if you don't want to do it by hand, you can always plug everything into Desmos. So there's my denominator. So now let's talk about that numerator and what the complement of this is going to look like. So we need to figure out the number of ways that we have no defective plates. So we're producing 40. 3 are defective. So we know that there's 37 that's not defective. And we want to choose 5 of those. So this is going to be 37 C5. So this is going to be 37 factorial over 5 factorial, and then 37 minus 5 factorial, or 37 factorial over 5 factorial, 32 factorial. So I could go back to Desmos and I could type that in. Get my keyboard to come up. I got 435,897. And then my probability of at least one that's defective would be equal to 1 minus the probability of none that's defective. So it's going to be 1 minus 435, 897 divided by 658,008. Now I'm just going to type this in the calculator. I've got one off screen to get a decimal approximation for this one. And I got about 0.338 for that. So approximately 33-ish%.